All right, folks, I'm going to run to the washroom for a second here. I'm going to share my screen with strong bases. Could you copy this down? And if people join and can someone just tell people as they join, they should copy this down? We'll talk about it when we get back. All right, so give me 3 or 4 minutes and I'll be right back. Copy that down. All right. Good morning, folks.
Hello. Hello, Mr. Patino.
I think I'm in a bit of a foul mood. I snapped at somebody in my last class.
What did they do?
I won't go into it, Alex.
Are you afraid that'd give me ideas?
No. All right. So, folks, I'm going to take some questions, I think, at the end of class. If anybody has some questions about homework questions or about the titrations or something. We're going to talk about bases today, and then we're done. Okay. Oh, sorry, we're done. We're done all the calculations today. So tomorrow we're going to learn about the last topic, which is non-mathematical for the most part. And then we're done acids and bases. So there'll be homework over the weekend, practicing questions on Monday if there are any, and then a test will come either Monday night or Tuesday. So that's what we're doing. We're wrapping things up, and there'll be a test after the weekend. Looking at the weather, we're going into a nice, it's like almost like summer now. It's going to be hard to focus, right? So do your best. All right. So this unit is called acids and bases. Most of our focus has been on acids. Now we're going to talk about bases. And so you kind of have to stop and ask yourself at the beginning of any question, what is this? Is this an acid question or is this a base question? Up till now, you haven't even had to say that because it was always an acid question. People who don't ask that will suddenly treat everything as acids and they'll get it wrong. Okay, so you have to stop now and say, am I looking at a base in this question or am I looking at an acid? There will be some clues. I'll point those out. So a strong base is in some ways very much like a strong acid. That's nice. Some very similar. It has complete dissociation, 100% ionization, right? So it's a very good electrolyte, just like strong acids. But strong bases have something that's unique, okay? Strong bases have something unique. When you look at their formulas, sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, strontium hydroxide. There are others, but you notice that every one of those formulas has hydroxide. And at the beginning of each formula, sodium, potassium, lithium, calcium, strontium, those are metals, right? On the periodic table, metals are on the far left side of the table. So you could say that a strong base is just a type of salt, a type of ionic compound, a metal bonded with hydroxide. Okay. So it's just like a salt. Now, how many hydroxides are in the formula? Well, it depends on the charge of the metal, right? So sodium and potassium and lithium, their charges were +1. Hydroxide's charge is -1. So they get 1 hydroxide each. But calcium and strontium, their charges are 2 positive. So the hydroxides are negative. Those 2 cations get 2 hydroxides each, right? So it's not magic. The number of hydroxides just makes the charge cancel out. So if you're 2 positive, you get 2 hydroxides. If you're 3 positive, you'd get 3 hydroxides. Okay. These are bases. So bases should produce hydroxide ions, not hydronium, right? So I can tell that because they have hydroxide, these are obviously bases. Sodium hydroxide is the one we used in the lab, right? That was the one we titrated, strong base. Now look at these equations. I'm not usually going to write an equation when I do a strong base problem. I usually don't. But if you do, these are the equations you'd write. And what do you notice that's a bit different? I said strong bases are unique. What's different is there's no water. We don't say plus water. We don't say something's donating or accepting. All we do is treat these like salts. They just break apart in water. Right? So notice there's no water in these equations. That's unusual in this unit. So the pH of a strong base solution. Don't bother writing that first sentence, but put the title down, pH of strong base solution. Mohammed, yes, I will be posting this, okay? Eid Mubarak. Okay, so calculate the pH of 0.010 molar sodium hydroxide. If you recall, finding pH of strong acids was very easy. And I even said, it's so easy, I wouldn't ask that as a free response question. Strong acid pH could be a multiple choice question. The same is true here. Strong bases are so easy to deal with, they would be multiple choice questions, not free response questions. So showing your work is not really needed for this, but I can do this question in my head. Can anybody else do that in their head? The pH of 0.01 molar sodium hydroxide? Anybody? The answer is going to be 12. How do I know it's 12? There's two things that make this easy. One is it's a strong base. So if it's a strong base, it ionizes completely. So I know that there's going to be 0.01 molar hydroxide, right? Since there's one hydroxide in this formula, 0.01 molar sodium hydroxide will have 0.01 molar sodium. I don't care about that. But it'll also have 0.01 molar hydroxide. That's what I care about. So the first thing I would notice is that the concentration of the hydroxide is 0.010 molar. It ionizes completely. Now, if this were not sodium hydroxide, suppose this were calcium hydroxide. Calcium hydroxide has two hydroxides in its formula. If it were calcium hydroxide, then you wouldn't get 0.01 molar, you'd get 0.02 molar, because there'd be two hydroxides for every calcium hydroxide. So be careful with that. I like to ask that on a test and catch people. If there's more than one hydroxide in the formula of the salt, you have to multiply by that number. So 0.01 times 2 for calcium hydroxide, for example. The other reason this could have been done in your head is because 0.01 is a very nice number. In scientific notation, 0.01 is 10 to the minus 2. So if it's 10 to the minus 2, then I know right away that the POH, remember this is hydroxide, the POH is going to be 2. And if the POH is 2, then the pH is going to be 12. That's how I could do it in my head. If you want to show your work, the POH is the negative log of hydroxide, so negative log of 0.010. If you can't do that in your head, then grab your calculator and you'll see it equals 2.00, equals 2. But the question wanted pH. I like to ask this on a multiple choice question. And when I do a multiple choice question, one of the choices will say 2. And there'll be people who choose it because negative log of 0.01 is 2. But that's not the pH. This is the POH. pH plus POH gives you 14. So if you want to find the pH, you simply go 14 minus that pH, the POH value. There's your 12 that I mentioned earlier. All right. So again, this is unlikely to be a free response question on a test. It's much more likely to show up as a multiple choice question. And remember, you're not finding pH at the beginning, you're finding POH. And then you have to get pH after that by subtracting from 14. Anybody have a question about this? All right. Have your data booklet open, please, to the Ka chart. If you don't have it open, do it now. Get your data booklet open to the acid chart. That page 9 or something. Page 8. Look at the bottom of page 8 in your data booklet. Underneath the acid chart, you'll see a weak base ionization constant chart. So strong bases are pretty straightforward. Let's look at weak bases. In your data booklet, there is a chart very similar to this one. Okay, so you don't need to copy this chart down. It's in your data booklet, the bottom of page 8. Weak bases are going to be very similar to weak acids. So assuming you know how to solve a weak acid problem, you're going to find weak bases to be pretty straightforward. When you look at the list of weak bases, look down below at the list of weak bases, the most important weak base, you'll probably want to highlight this, is ammonia. Ammonia is the most common weak base, NH3. When you look at the other weak bases, you notice they pretty much all have nitrogens with hydrogens, right? NH2, NH, N2H4, NH2, NH2. That means these other weak bases are derived from ammonia. Ammonia was NH3. These others are created from ammonia. So ammonia is the most important weak base. Most other weak bases are going to simply be derived from ammonia, created from ammonia. Acids have Ka values. So bases will have Kb values. These bases are weak bases because their Kb values are all very small. Now be careful when you read the chart. These are Kb values. Over on the right, it shows us the formulas of the conjugate acids of each base. Bases accept hydrogen ions, so if you just add a hydrogen ion to each of those bases, you get these acids. These are their conjugate acids. And then it tells us the Ka value for each of those conjugate acids. So when you're looking up a Kb value, be sure you're picking the right numbers, the numbers from the Kb list, not the numbers from a Ka list. In your data booklet, I didn't do that. In the data booklet, I just gave you Kb values to help prevent that. But on a Google Forms test, I could give you this, and then you have to be careful you're choosing the right thing. So let's see if we can apply what we've learned about weak acids to a weak base. The calculation is going to be very similar. So here's an example. Find the pH of 0.25 molar ammonia. Go ahead and start the question. by writing a balanced equation. Don't go any further, because if your balanced equation's wrong, you're going to screw up everything else. The mistake most people will make, if they make a mistake, is that they'll write a balanced equation which treats the ammonia as though it were an acid, just because they're so used to doing acid problems. Ammonia is not an acid. Ammonia is a base. So ammonia does not donate hydrogens. Ammonia accepts hydrogens. So think about that as you're writing the balanced equation. The NH3 is going to take a hydrogen from water. So NH3 reacts with water, and the NH3 takes a hydrogen from the water. So what will be your products?
OH negative and NH4.
NH4 positive, right? Does that make sense?
Yep.
Yeah, very good. So, and notice something else. This was a base. Bases should produce hydroxide. So if you don't write hydroxide as a product, stop. You're doing something wrong, right? All right, go ahead. Fill in your ice table. Say stuff on the side of the ice table. Do exactly what you would do in a weak acid question. So you should have an ice table and a statement on the side of it that looks something like that. Your ice table should look exactly like that, and your statement on the side should be something like that. Ammonia is a weak base. You looked up in your data booklet the Kb value for ammonia. And because it's a weak base, just like a weak acid, it does not ionize completely. So we use X's in the table. And you know what's coming next. We're going to do the equilibrium expression. We're going to put the algebra in. If you have a graphing calculator, you can use your solver. If you don't have a graphing calculator, you'll use the assumption method, the approximation method, and you're going to go find X. In a test question, I would probably give you the Kb value. And that's where I get frustrated when I see people make mistakes, because in the question, I'll say Kb equals, and then they write an equation that treats the ammonia as though it were an acid. They say it makes hydronium, but it says Kb equals. It's a base, right? So it has to accept a hydrogen, not donate it. Put your algebra in. If you're doing the approximation method, be sure you're stating your assumption. It should say something like that. Because this Kb value is small, X is going to be small. Therefore, let's assume that X is much less than 0.25. If X is much less than 0.25, then our equation can be rewritten in a slightly easier way. We get that 1.8 times 10 to the minus 5 is approximately equal to X squared over 0.25. Instead of 0.25 minus X, we just have 0.25. Pick up your calculator and find out what X equals. Okay, so did you get that if you're using the approximation method? Did you get that as your first X? If you didn't, tell me and I'll help you with your calculator. To find your second X, your second approximation for X, you take this first answer and you put it back where we ignored it. So you put it back on the bottom over here, 0.25 minus 0.0021. You pick up your calculator and you subtract those. You'll times by the KB value and you'll square root your answer. Your second approximation turns out to be the same as the first. So we're done. If you didn't get that, let me know and I'll help you. People who used the solver, I hope that's what you got, 0.0021. In the acid unit, this number was our hydronium, so we just went and found pH. This is not an acid, this is a base. So we look up at the ice table and we notice that the X is the hydroxide concentration. So we're going to go find the POH, and then we'll get the pH. So the POH is the negative log of hydroxide, so negative log of 0.0021, 2.68. And now that you have POH, you can find pH. Remember, if you're doing a base question like this, bases have to have pHs that are high, right? So the pH has to be above 7. If it were a multiple choice question, what's the pH of this base solution? Any answers that are less than 7 or even 7, those are all impossible. You just cross them out. Has to be something above 7, the pH value, if it's a base. So 14 minus that, the pH of this weak base solution is still pretty high. Why is this such a high pH value if it's a weak base? It's so high because this concentration is pretty big. 0.25 molarity is a pretty big concentration. Anybody have a question? Anybody not able to get something on their calculator? All right, would you quickly calculate the percent ionization? This base is a weak base, so it does not ionize completely, but what percent did ionize? Okay, go ahead and calculate that. What is the percent ionization? You take your X value. We said it was equal to hydroxide earlier. It is. But it's also, if you look back at the ice table, X is right here in the middle. It's the amount of the ammonia that ionized. So take your X and divide by the starting concentration and times by 100. So 0.0021 divided by 0.25 times 100, you get an answer less than 1%. It's 0.84%. Okay, so it's a weak acid. It ionizes just a little bit, 0.84%. All right, we're going to end today with this, and then we'll take some questions from homework. I want you to make this title a little bit clearer, okay? Instead of just saying this, it's the relationship between Ka for an acid and Kb of its conjugate base. Would you put that down? The relationship between Ka of an acid, Ka of an acid, and the Kb of its conjugate base. The Kb of its conjugate base. So this is a very specific relationship. It's not just any Ka and any Kb. The Ka of an acid and the Kb of its conjugate base. Now, I could just tell you the relationship, but rather than do that, let's derive the relationship. So we're going to consider a weak acid, HF, and its conjugate base. What's the conjugate base of HF?
F negative.
That's right. So we're going to be using HF as an acid and F negative as a base. Yeah. Do you have a quick question? I can quickly go over there if you want. All right, give me 1 sec. Okay, folks, I'm just going to run out for 1 second. I want you on the left side of your page, you notice how I have a line down the middle, do the same thing. On the left side of your page, write the balanced equation for HF, the weak acid, in water. And on the right side of your page, do the same thing, but for the base, for fluoride in water. And underneath both equations, write their equilibrium expressions. Okay, so on the left side, HF reacts with water. On the right side, F minus reacts with water. And then write their equilibrium expressions underneath each one. I'll be back in 2 minutes. All right, so those are your two equations you should have written. HF is an acid, so it donates hydrogen to water. And so water turns into hydronium. and HF turns into fluoride, which is its conjugate base. On the right side, fluoride is a base. So it takes a hydrogen from the water, and the fluoride turns into HF, its conjugate acid. And then the water, which gave away a hydrogen, becomes hydroxide, OH minus. Underneath each equation, you've written the equilibrium expression. On the left side, you should have said Ka equals, and on the right side, you should have said Kb equals. There's an acid on the left and there's a base on the right. So your equations should say that. All right, so now in arithmetic, there are 4 basic operations. You can add things together, you can subtract things, you can multiply things, you can divide things. Which of those 4 operations would be the best thing to do with these 2 expressions? Should we try to add these expressions together? Should we try to subtract them? Should we try to multiply them? Should we try to divide them? Which one of those just looks like it would be a smart thing to do? Riley, what do you think?
Would you multiply it?
And what would be your reason for that?
Well, both of them are like sort of fractions, so you could just cross multiply them.
What do you mean cross? No, you wouldn't
No.
cross multiply, no. Cross multiply means something very specific, right? So no, unless you just said something the incorrect way. Taylor, what do you think? What would you do with this?
Multiply or divide, but I don't know why.
Okay. Finn, do you have any idea?
Nah.
The answer is not in any way related to chemistry. The answer is just math. Okay, there's a reason mathematically that we should do something. It's not anything to do with chemistry. Abby, what do you think?
I'm not sure.
Okay, well, in your head, look at them and say, if I were to add those, if I were to subtract those, if I timed those together, if I divided those, when you think of it in your head like that, do any of those 4 choices sort of say, hey, that would work out nicely?
Mr. Padno,
Yeah,
would you multiply because then you can cancel the HF and the F?
exactly correct. Okay, we're going to multiply the 2 expressions because when you multiply, the fluoride on top and the fluoride on the bottom cancel out. Now, Riley, I'm not sure if that's what you meant earlier, but that's not called cross-canceling or cross-multiplying, rather. HF on the bottom and HF on the top cancels out, right? So we're going to multiply them together. So take the Ka of the conjugate of the acid and times it by the Kb of the conjugate base. So take the expression for Ka and times it by the expression for Kb. And as Ethan just pointed out, fluoride cancels, HF cancels, and the stuff that doesn't cancel, hey, look at this. It's not just that it's simpler, it turns into hydronium times hydroxide. And what is hydronium times hydroxide? Hey, that's Kw, right? So algebraically, it was nice because things canceled out. But then when we look at it again with chemistry eyes, we realize that after things cancel out, you have Kw. So there is the relationship between an acid's Ka value and the conjugate base Kb value. Ka times Kb will always give you Kw. But please understand, this is not just some randomly picked acid and some randomly picked base. This is an acid and then its conjugate base, or a base and its conjugate acid. They have to be conjugates for this to work out. All right, so make sure you highlight that equation at the end. Ka times Kb equals Kw. Okay, now I'm going to make two observations about this. Okay, so two observations. One is purely mathematical. Does anybody recognize what kind of mathematical relationship that is? If you say Ka times Kb is Kw, what does that mean about Ka and Kb mathematically?
They're inverse.
Very good. Okay, so say that. Ka and Kb are inversely related. Inverse. Does anybody need that spelled? Inverse. They are inversely related. Now, if you just write that, but you don't know what that means, it's not helpful. What does it mean if they're inversely related? It means when the Ka gets bigger, then the Kb of the conjugate base needs to get smaller. So when they multiply, your answer is the same, Kw. So when Kas are bigger, the Kb of the conjugate base is smaller. That's what inverse means. Now take that mathematical relationship and translate it back into chemistry. What does it mean when we say a Ka is bigger? We mean the acid is
Stronger.
And then if the Ka is bigger, we said the Kb would be smaller. So what would be the chemistry way of saying that? When you have a stronger acid, its conjugate base will be weaker. The stronger an acid is, the weaker will be its conjugate base. That's what that means from a chemistry perspective. The acid gets weaker, its conjugate base gets stronger. If the acid gets stronger, its conjugate base gets weaker. So the strongest acids on the Ka chart, the ones at the top, their conjugate bases must be incredibly weak because those acids ionize completely. So their conjugate bases are like super weak. Okay, now we can use this equation like we just talked about qualitatively. We could say if this acid is stronger than this acid, then which conjugate base is stronger? Well, that's related to what we just said. Or we can treat this mathematically. Now in slot A, I actually got kind of disillusioned with my grade 12 students because 10 students in a row that I asked couldn't answer the simple mathematical equation. It drove me crazy. I'm going to give you a Kb value, and I want you to calculate the Ka value for its conjugate acid. So for example, over here we said ammonia had a Kb of 1.8 times 10 to the minus 5. Well, calculate the Ka for its conjugate acid. Grab your calculator and do that, or show your work on paper. If the ammonia has a Kb of 1.8 times 10 to the minus 5, what is the Ka for its conjugate acid? Well, the answer is right there in this chart, but can you get it on your calculator? Can you figure out that it's 5.6 times 10 to the minus 10? Okay, so all you're doing mathematically, let me stop sharing this. So mathematically, this is very simple. You're simply saying to yourself, if Ka, can you see what I'm writing here, folks? Let me zoom in on this for everybody. So Ka of an acid times the Kb of its conjugate base has to give me Kw. So I just said to you, the Kb of ammonia is 1.8 times 10 to the minus 5. What's the Ka of its conjugate acid? So Ka would equal what? If you just rearrange that equation.
Kw divided by Kb.
Thank you. Is there anybody who doesn't see why that's true? If 2 times 3 is 6, well then 2 equals 6 divided by 3, doesn't it? So if Ka times Kb is Kw, then the Ka is the Kw divided by the Kb. So that means it's going to be 1.0 times 10 to the minus 14, that's the Kw, divided by the Kb of the ammonia, which was 1.8 times 10 to the minus 5. Pick up your calculator and do that. In the middle of May, I still had people in slot A who didn't know how to do scientific notation on their calculator. How could that be in the middle of May that we don't know how to do scientific notation on a calculator? Your answer is supposed to be 5.6 times 10 to the minus 10. Is there anybody who cannot get that on their calculator? Okay, take a quick look at your Ka chart. The Ka for benzoic acid is 6.4 times 10 to the minus 5. What is the Kb for benzoate? So this Ka is for benzoic acid, C6H5COOH. What is the Kb for C6H5COO minus, the conjugate base of benzoic acid? By the same logic that we just used, the Kb would equal Kw divided by Ka. So grab your calculator and Kw divided by that Ka value, what do you get? (1.6 times 10 to the minus 10), I hope is what you got. All right. So give me a Ka value and I can calculate the Kb value for the conjugate base. Give me a Kb value of a base and I can calculate the Ka value for its conjugate acid. That's partly why the Kb chart is so much smaller than the Ka chart, because any of these acids here, I don't need a Kb chart for their conjugate bases. I can calculate the Kb values for all of these conjugate bases by doing Kw divided by their Ka values. So you don't need to tell me all of their Kb values. I can calculate them. These weak bases are derived from ammonia, so they're not quite the same as these conjugate bases over here. So you have to give me a separate table for those guys. Okay? But again, you didn't need to tell me their Kb the Ka values of the conjugate acids because I can calculate them from these Kb values. Okay. All right, I'm going to stop there, folks. I got a few minutes left. Does anybody have, I'm going to quickly do attendance, but while I'm doing attendance, if you have questions, look them up from your homework or look them up from the titration homework. If you have a question, get ready to ask that, and I'll take a few questions before we're done.